Good morning.
Morning, sir.
Yeah, so welcome back. Uh, Last class we uh, discussed about the various noise models. I had actually given you a homework. It is only to think and let me know what is the answer. So anybody with the answer, if you want, you can chat on the chat window. So the question was, I had shown you an image and what would be the histogram of that image. Anybody with the answer? This is the test pattern. Is the slide visible? Is the slide visible? Hello, can somebody respond? Okay, so Rakshita says yes. Um, yeah, so what do you think is the histogram of this image? I have also told you that this part of the image has got one gray level, and this part of the image has got another gray level, and this part of the image has got another gray level. Maybe you can assume this as some 50, this may be some 100, and this may be some 150. So what will be the histogram of this image? Any answer? Nobody has thought of it. Okay, so let us move on. What I'll do is I'll just show a simulation on MATLAB. I have generated a similar image, slightly different for some specific reason. Let me just show you the. Okay, so it's almost same as you could see. Only thing is, instead of a circular region here, I have taken it as a square region because it's easy to generate this type of image. Defining a circular region here needs some additional implementation. So I just thought I can just go for this. Now notice here on the left side here, I hope you can see the pixel information. Are you able to see this on the left here? Pixel info intensity. Are you seeing? Yes. Okay. So if I move my cursor in this region, you could see that all the values are 200. All these values are 200. And in this region, all the values are 100. And in this region, all the values are 50. Okay. Now what histogram means is on the x-axis, you will have the gray level. On the y-axis, you will have the number of pixels having that particular gray level. So what it means is there are so many pixels with gray level 50. There are so many pixels, all these pixels, you have to count how many are there with 100 and all these pixels with 200. So obviously the histogram would be three spikes like this. one spike at 50. That means you will have so many values of gray value 50, so many values of gray value 100, and so many values of gray value 200. So you will have three spikes, one at 50, other at 100, other at 200. The reason because in this image you have only three gray levels. I have 50, I have 100, and I have 150. So when I plot it as a one-dimensional plot, that is histogram, I will be having only three spikes like this. Okay, is this clear? Any doubt? I thought somebody will answer this question, but I don't know. Maybe you have not thought of it. Is this clear? Any doubt?
Sir,
Yeah,
it's clear, sir.
yeah. Nitin says it is clear. Okay, clear. Okay. So I have three spikes now. Now, what is the use of this? Let us go back to our discussions. The use of this is I'll use this as a test pattern. Now, when I corrupt this with a different type of noise, I'll just again do that by okay, by plotting the histogram. I'll just see how does the shape looks like. I repeat, corrupt this or add different types of noise. You know, in the last class we discussed about Gaussian noise, Rayleigh noise, gamma, exponential noise, salt and pepper type of noise, uniform type of noise. Okay, so MATLAB has commands to generate all these type of noise. I can show the simulation later. Now if I take such an image, and plot its histogram, okay, corrupt these images by those type of noise. Now carefully observe this. Okay, with if I don't give you this shape or this okay, name, all the three are almost looking same to you. Am I correct? I don't think you can say this is corrupted with Gaussian noise, this is corrupted with Rayleigh noise, this is corrupted with gamma. That means if I don't give the name here, you cannot say that each one what is the type of noise. That means just by looking at an image, I cannot plot. Sorry, I cannot identify which type of noise it is. Okay. Of course, a special case is the salt and pepper type of noise, because salt and pepper type of noise visually you can say you can observe and say it is salt and pepper. Whereas other type of noise, I don't think anybody can recognize that this is corrupted with gamma noise. But if I plot the histogram, observe, remember I said if it is a pure image like this without noise, you would be having a an impulse here, another impulse here, and another impulse here. One for this, one for this, one for this. But now since it is corrupted with noise, you can now observe the shapes. I am sure that all of you can see a Gaussian type of curve here, a Rayleigh type of curve here. Observe, Rayleigh looks like this. Okay, it is right skewed. Okay, and in this case, a gamma type of noise, which is visible here. So you can observe, and also these are the next noise. So you can see an exponential shape here, and this is uniform noise. You can see a uniform distribution approximately, because this is a digital image. You cannot exactly have it to be constant like this. Some values will definitely change, but you can just see the approximately it is a uniform distribution. And in this case, you would be definitely seeing, I don't know whether you can notice, there is a there is a spike here at 0. Okay, because this is for the pepper type of noise. There is another spike here at 255. This is for the salt type of noise. So along with the spikes that you have for these values, you will also have the spikes for the noise. But anyway, if I was given this I would have directly told without even plotting its histogram that this is salt and pepper type of noise. That means with some expertise in image processing, I think I can definitely say this is corrupted with salt and pepper type of noise, because you could see white dots and black dots. But definitely these two and also these three, no way I can just look at the image and say what is the type of noise that is corrupted. Okay, let me repeat what I have told. We took a test pattern of this nature, corrupted with different type of noise and plotting its histogram. If the histogram of this is plotted, I have already demonstrated, you will get two, three spikes, one at this value, one at this value, and one at this value. Now, when it is corrupted with noise, you could see a shape of Gaussian distribution here, a Rayleigh distribution. Let me demonstrate this using MATLAB. Of course, MATLAB cannot, in fact, uh, uh, generate all types of noise. I'll just do it for Gaussian type of noise. So I'll continue. Okay. So observe, this was the original image and this is the histogram. You have three spikes. Are you able to see the window?
Yes, sir.
Okay. And this is image corrupted with Gaussian type of noise. How can I justify that? Just look at the code. Im noise is the command to add noise to an image. So I have given within quote Gaussian. So if I give salt and pepper here, it will add salt noise. If I give uniform here, it will add uniform distribution. Okay. And this is the mean of the noise. Mean is taken to be 0, and this is the variance. If you increase the variance, obviously you know. Let me just try to increase the variance and run it again. So you can see the noise has increased, and you can see the distribution also. Okay. So this is too much of noise. Okay, this was the original with noise equal to some variance of 0.001. So you can notice here, this is a Gaussian distribution. So by just looking at the histogram of the image, I can say what type of noise it is. So the in fact, uh, the discussion that we have here is, if I use such type of test pattern, this is only to understand how noise can be estimated. Okay, this is only to understand how noise can be estimated. So uh, what I had to learn from this experimentation is, if I want to know what type of noise is corrupting the image, go to such type of smooth region. Okay, in the image, see, this is a test pattern. You cannot expect the real images to be like this. Definitely real images will have a lot of variation. So the advantage is, if I just try to take the smooth region in the image, plot its histogram, the shape will tell me whether it is Gaussian type of noise, gamma type of noise, or Rayleigh type of noise. So that is the in fact the moral of this discussion. Okay, I repeat, I can take a smooth region in the image and then plot its histogram. The shape will give me what type of noise it is. So at least you can determine what type of noise it is. Once I determine the noise, for example, if I determine that the noise is say Gaussian, so then the immediate thing that you need to know is what would be the mean and what would be the variance. Normally the mean of the noise will be 0, so the only parameter that you have to determine is variance. So by finding the variance, I have determined the noise, and once I know the noise characteristics, it is easy to design a filter to remove it. Okay, so That is what we discussed, we understood from this experimentation. Now let us try to see another type of noise called periodic noise. Okay. Normally, when there is some electrical electromagnetic mechanical interference during acquisition, okay, usually this type of noise is going to occur. And this type of noise is actually spatially dependent. It depends on okay, the the location of the pixel. And see, I don't know whether you can really notice a regular structure of this noise. I hope you can observe that when I move along the x direction or move along the y direction, the pixel value is increasing, becoming maximum, and decreases. So this is a type of periodic noise. In fact, it is a sinusoidal signal. The noise here is a sinusoidal signal. Why I say sinusoidal? Because it increases maximum and then it decreases. So if you zoom this, I think you will definitely notice that. So there is a periodicity in the noise here. Okay. Can somebody tell me what is the Fourier transform of a sinusoidal signal? You can chat if you want, or you can, if you don't respond, I have to go by name. Fourier transform of a sinusoidal signal, which you have done in third semester signals and systems. When I take a Fourier transform of a sinusoidal signal, what do I get? Okay, I'll start with the first name itself, Nikhil Kumar.
Yes, sir.
Okay, what is the Fourier transform of a sinusoidal signal? It's a very straightforward question that I'm asking you. Sine signal,
It's a cosine.
Fourier transform of a sinusoidal signal. Priya, Priya HM.
Sir,
Yeah. What is Fourier transform of a sinusoidal signal?
mm,
Somebody says Suresh, I think is telling impulse. Okay. Yeah, you are correct. So where will you get this impulse? How many impulses you'll get? If you consider the Fourier transform, you have to show, yeah, two. One at the positive frequency, other at the negative frequency. Okay. So Fourier transform of a sinusoidal signal is two impulses, one at positive frequency and other at negative frequency. Okay. Actually, in this image, you have sinusoidal signal along x direction. That is why you could see periodicity here. You also have sinusoidal signal along y direction. You have sinusoidal signal along the diagonal direction. That means the sine signal is varying along x, along y, along the diagonal directions. So when I take the Fourier transform of such an image, hope you are observing some dots here, white dots. Because two impulses, if I show it as an image, you will get it as a white dot. This we discussed in the last class. Okay. So do you see a white dot here and a white dot here? This place and this place. A white dot here and a white dot here. Again a white dot here and a white dot here. Similarly along the diagonal direction. Is it visible on this image? Yes. Rakshita says visible. Okay. So this is because this image is corrupted with a periodic type of noise, that means a sinusoidal type of noise, and all of you know that sinusoidal signal, the Fourier transform is two impulses. So I could see these impulses. So if I just plots a Fourier transform of such an image, I have identified the noise. Now the only requirement is I have to remove this noise. How we should remove this noise, we shall discuss it later. Okay. So periodic noise is one type of noise which will actually in fact corrupt the image, and it can be easily detected by just using the Fourier transform of an image. Sorry. Okay. So if I want to remove it, obviously I should use a filter, and we will discuss about this filter a little later, how we can remove such type of periodic type of noise. Okay. Now after having identified the shape of the noise spectrum, how do we estimate noise? Because unless I determine the parameters, I cannot use any filter. Okay. Now let us try to discuss estimation of noise parameters. Just now I told if it is a periodic type of noise, just plot the spectrum and it will give me the noise parameters. In fact, it has by observing the frequency spectrum, I can determine the periodic noise. Okay. Suppose if it is some random noise and I don't know the PDF, there are many cases. Case one is imaging system is available. That means I have a camera and I have captured an image and it is noisy. The camera is with me. Okay. So if I have the camera with me and I don't know what is the type of noise it is going to add, the best thing to do is use that camera which is adding some noise, capture images of flat environment. Why should I say flat environment? Just now you saw that if I plot the histogram of the flat environment, I will find the shape of the noise. Okay. So if the camera is with me, I can use that camera and capture something like this. See, for example, this is a smooth region. So I'll use my camera and capture this. So and then plot its histogram. The shape will tell me what type of noise it is. Okay. What if I don't have the camera? The scenario is, for example, satellite imaging. The camera is on board a satellite. You don't have the camera with you. So in such cases, I have only noisy image. I don't have the camera with me. Okay. Again, I'll go back to the same, in fact, the test experiment. We understood that a smooth region of an image, if the histogram is plotted, the shape will tell me what type of noise it is. So we will we will take a strip from the constant area when noisy images are available. Only noisy images are available. I don't have the camera with me. From that image, take a strip from the constant area. The bigger this area, the better. Okay. The larger the area of the constant region you get, the better would be the estimation. Then plot the histogram and observe it. Okay. Once I know the shape, then you can find the mean and variance of that particular noise. There is an example given here. What is done is from this image, a small strip is taken somewhere here. Okay, what you see is that strip here. So for that strip, the histogram is plotted. So obviously we can observe that this shape looks like a Gaussian shape. So this image is corrupted by Gaussian noise, and this shape is like Rayleigh distribution. So this image is corrupted by Rayleigh noise, and you can see that this is uniform. So you can recognize that this is uniform. That means I can say this is exponential. Sorry, this is uniform, and this is of course salt and pepper. We are not. So we have three of them. We have done it, not all. So if noisy images are available and I don't have the camera, this is the best thing. So when I give you a noisy image, you can just take the constant area in that image, plot its histogram, and then you can observe the shape. It will tell me what type of noise it is, then measure mean and variance. Okay. Now the next question is, how will you measure mean and variance? All of you know the formula for mean and variance. This is the formula for mean and this is the formula for variance. So this is straightforward. The value of the pixel, the probability of occurrence of that pixel. Okay. Can somebody tell me how will I calculate the probability of occurrence of a pixel? How do you calculate that? Anybody? How will you calculate probability of occurrence of the pixel? How will you get this? Sindhu Kumari, Sindhu Kumari ND. Unmute and speak. Sushma S. Sushma, can you
Yes, sir.
speak? Yeah. So the question that I have asked is, how will you calculate probability of an occurrence of a particular gray value or a particular gray level? How do you calculate probability of some event? What is the formula for finding probability?
So
Anybody?
required probability by total probability.
No, no.
Required.
Okay, in this case, what I am trying to do, you have understood. What I am trying to do is I have just taken a small strip here from the original image, and this should be a uniform region because you know why it should be uniform. Now I have gray values here. Okay, so the gray values are there, and so I need to calculate probability of each of the gray value. Shivam, can you try?
Sir, Gaussian PDF.
No, no. What I want is how will I calculate probability of occurrence of each of the gray level in this particular small strip. I have given you a small image. I want to calculate probability of occurrence of each of the pixel. You have done a problem in histogram equalization. How did you find the probability values? No idea. Okay. Yeah. Yeah. I don't want to comment on these things. You know where do you stand. Let me just move on. Okay. So histogram. Yeah. Somebody is. Yeah. NK by MN. What is NK here? Uh, who is it? Rakshita, I believe. Yeah. Nk is, I assume that it is n suffix k, so it should be the number of times each of the gray level is occurring. Yes, yeah, Rakshita is correct. So what I do is, in this, I'll just count how many times each of the gray level is appearing, divided by the total number of pixels in this small strip. Okay, that is what I have to do. Total number of pixels in this small strip, depending on the size of this strip, and each gray level how many times it is occurring, and that will give me the probability. So x p of x, as you know, is how you can find mean, and of course once I find the mean I can use this formula and find the variance. Okay, so let us try to understand it. We are trying to do case 2. Case 1 is imaging system is available, capture images of the flat environment. Case 2 is I don't have the imaging system, I only have the noisy images. Take a strip from the constant area and draw the histogram. Okay, now you have got the shape of the distribution just like this. The shape of the distribution is known, but you need to find mean and variance. So to find mean and variance, use these two formulas. Okay, from that small strip, calculate the mean by using these formulas. Now you have seen in the expression here, in fact, when I was discussing, once I get the mean and variance, I know Gaussian distribution. So in case of Gaussian distribution, nothing more to be done because you have already determined mean and variance. Whereas if it is say Rayleigh type of noise, you have determined mean and variance, but you want A and B to calculate, to define the probability distribution curve. So what you need to do is use this mean and variance. There are two unknowns and two equations. So there is one equation for in terms of A and B, second equation in terms of B. So what you can do is, in fact, in this case, since variance is known, I can find B and use that B here, and mean you can calculate A. So you can find the constants A and B. Even here also, mean and variance are related by A and B. So from mean and variance, determine A and B, and that will give me the probability distribution. So that's exactly what it means. Okay, so once I find mean and variance, for Gaussian and uniform distribution, they are directly giving me the values. For Gaussian, sorry, for uniform distribution, you can find the A and B from this mu and sigma. Okay, so this is how I can find the noise. So what we have understood so far is, if a noisy image is given to me, how will I find the noise? Let me just quickly go through it. The first step is, first, if the noisy image is given, take a small strip, in fact a strip where the area is constant or it is a smooth region, plot its histogram, and histogram will give me the shape. Then find the mean and variance by using this formula. Use that mean and variance formula to calculate the constants required. That will give me the estimation for noise. Now once that is done, how we can do the restoration? Okay, now as I told you in the beginning, let us just try to make some assumptions that there is only in fact degradation because of noise. You don't have the blur coming into picture. This is an assumption again. Okay, now in fact I have already explained it, but let me ask you that question again. Suppose if I had to neglect the blur degradation function, what should be the point spread function of this system? Okay, I have already explained this. What should be the PSF of the in fact the system, so that my image here appears at the output without any blurring. Output here is same as the input. What should be the PSF? Just in the previous class we discussed about it. When can I expect the output of a system to be same as the input? What should be the impulse response or the point spread function? Yeah, impulse. Somebody says delta function. Yes, Nitin says delta. Sindhu says impulse. Delta. Okay. Shivam says delta. Yes. So if this is a delta function or if it is an impulse, then convolution of f with an impulse is f itself. So that is why the equation, remember when we wrote the model was this. G is h convolved with f plus eta, but now by assuming that there is only noise, no blur, it is only f plus eta because this is delta function. So f convolved with delta is f plus noise, I'll get g. So I have a noisy image here. So if I go to the frequency domain, it is this. Even though this is not actually true because you cannot expect a Fourier transform of a random signal. Just mathematically, this is what it means. Okay. So it looks like subtracting, see for example, if I want original image f, it is easy to find capital F here. How I can do it? I'll take this to the other side. So it is G minus N, thereby it is F. So if I subtract noise from the degraded image, I will get the original image. This looks very simple, but this is true only in types of periodic noise. Other type of noise I cannot directly use this formula because first of all this is not an easy thing. Okay. So there are many filters. In fact, this we have already discussed. Some of it is already discussed in previous unit. Uh, in fact, your box filter is this. Okay. So let me just explain this with probably an equation. Okay. So is the one not visible?
Yes, sir.
Okay. So observe this equation, arithmetic mean f hat is 1 by mn summation g of st over a range st in the range s of x, a window. Okay. So let me just consider that window to be maybe a 3 cross 3. Okay. So m is equal to n is equal to 3. The window size is 3 cross 3. So what happens is your equation here, if you observe, this is 3 into 3, so it is 1 by 9 summation over that range. So looks like this. So 1 by 9 summation all those values over that particular 3 cross 3 kernel. Okay. So over 3 cross 3 kernel. So if you observe, this is a kernel like this. What is this filter? We have already done. What type of filter is this? This we have called it as a box filter, which is an example for low pass filter. We have discussed in the previous unit itself. It is a low pass filter. Okay. So I can change the kernel size. For example, instead of m equal to n equal to 3, I can use 5. Then this becomes 1 by 25. That means this will be a 5 cross 5 kernel. Okay. So if say m is equal to n is equal to 5, then I'll have it as 1 by 25 and all of them as 1. So this is a low pass filter. This is a box filter. It smoothens edges, but it smoothens noise. We have seen this in the last class, in the last unit. Okay. So an arithmetic mean filter can be used to remove noise. Okay, so one of the filter that I can use is an arithmetic mean filter. F hat is the filtered image. G of x comma y is actually the original, noisy image. So I can just apply a simple smoothing filter, and the window size can be increased. By increasing the size of the window, you can probably have more and more smoothing of noise, but that is at the cost of smoothing edges. All of you know about it. I have also shown a simulation earlier in Unit 2. So this is one type of filter that I can remove noise. There is another type of filter called geometric mean filter. Carefully observe the difference here. F hat is the filtered image. Instead of summation here, there is a symbol here. This is a symbol for product. This is the symbol for product, G of st, and after finding the product, you are raising it to the power of 1 by mn. Okay. So for example, if you take a 3 cross 3 here, so it is a product, sorry. So your f hat of x comma y will be, let me assume that m is equal to n is equal to 3 again. It is a product over that region G of st, and you have to raise it to the power of 1 by mn, and mn here is 9. Okay. So the respective value of the pixel in that particular region, it has to be raised to the power of 1 by 9. That is what you are doing. This is a product symbol. For example, in a specific range, assume that you have all the values same. Let us assume that all the values are same. Okay. So what you will be doing here is, by using this filter, if you want to filter it out, so you have to raise 10 to the power of 1 by 9 into 10 to the power of 1 by 9 into etc. 10 to the power of 1 by 9. Okay. Since all the values are same, and there are 9 such values, as you can see here, 9 values are there. Therefore, I'll get what would be the value you will get? 10 to the power of 1 by 9 to the power of 9, which will be equal to 10. So whenever the image is smooth, it copies it as it is. Okay. So if the image has got some noise here, accordingly it is going to filter and give me an equivalent value here. So I hope you understood how geometric mean filter works. The difference here is, in arithmetic mean filter you are adding the pixel values, whereas in geometric mean filter you are actually raising it to the power. Is that clear how this works, geometric mean filter? Any doubt? Any doubt? No doubt. Okay. Yeah. So uh, definitely arithmetic mean is just doing a simple addition and dividing it by 9. So it is the simplest one to implement. It's very easy. In fact, we have done this. Okay. By implementing this is not directly possible. You need to develop a code, but this I think by just using simple convolution you can do it. In both the cases, noise is reduced at the cost of blurring. All of you know that no doubt the noise is removed, but this is at the cost of blurring. Comparatively, geometric mean in fact tends to lose less image detail. That means when it comes to the edge information, preserving edges, geometric mean is better when compared to arithmetic mean. So that way geometric mean is but slightly better than arithmetic mean. No doubt it smooths the noise as compared to arithmetic mean, but when it comes to preserving the image details, that is the edge information, geometric mean is better. Okay. Yeah, so there are many other filters like harmonic, contra harmonic, which we will discuss in the next class.